Tonight everything begins with a mystery hidden in plain sight. Planets spin, moons spin, stars spin. Entire galaxies turn slowly through the darkness of space. Even the giant clouds of gas that give birth to stars are rotating. Everywhere scientists look, motion appears woven into the fabric of the cosmos itself. For centuries, no one fully understood why. Why should almost everything in the universe be spinning? Where did that motion come from? And why has it survived for billions of years? In this journey through space and time, the story follows the hidden force that shaped planets, stars, galaxies, and perhaps the universe itself. From the first moments after the Big Bang to the rotation of Earth beneath every living thing, the answer reveals one of the most fundamental rules in nature. If this kind of deep space exploration is fascinating, take a moment to like the video, subscribe to the channel, and join us for more relaxing journeys through science, space, and the history of the cosmos. Now, as the universe slowly turns around us, the story begins with a simple observation: everything spins. The observable universe stretches across distances so large that ordinary experience offers no direct comparison. Light travels across immense regions for billions of years before reaching telescopes on Earth. Within this enormous expanse, matter is not distributed evenly. Galaxies gather into groups, groups gather into clusters, and clusters connect through vast filaments that form a structure often called the cosmic web. Between these regions lie enormous volumes of comparatively empty space. From the largest scales currently observed, the universe appears orderly in some ways and irregular in others. It expands steadily in all directions, yet within that expansion, countless objects move, orbit, drift, and rotate. Motion appears everywhere. Galaxies travel through space. Clouds of gas shift under gravity. Stars circle galactic centers. Planets travel around stars. Moons orbit planets. Even before examining these smaller systems in detail, one broad feature becomes apparent. Nature rarely remains perfectly still. The universe is a place of continuous movement. Astronomers spend many decades measuring these motions. They observe tiny changes in light arriving from distant objects. They study how wavelengths stretch or compress as galaxies move away or toward an observer. They map positions across large regions of the sky and compare observations gathered over many years. Through these efforts, a picture emerges of a dynamic cosmos, in which movement is not unusual but fundamental. At the largest observable scales, however, a remarkable pattern appears. The universe as a whole does not seem to rotate like a giant wheel. Measurements of the cosmic microwave background, the faint radiation left from the early universe, indicate a cosmos that is remarkably uniform in every direction. Observations suggest no convincing evidence that the entire observable universe spins around a central axis. Scientists have searched for signs of such motion through detailed studies of large-scale structure and ancient radiation. Thus far, the evidence indicates that the observable universe expands but does not rotate as a single object. This finding is important because it separates two different ideas. One concerns the universe as a whole. The other concerns the countless structures that exist within it. Even though the observable universe shows no measurable global spin rotation, appears repeatedly among the objects that fill it. The absence of universal rotation does not prevent local rotation from emerging. In fact, local spinning motion becomes one of the most common features in astronomy. The larger structures visible through telescopes reveal this tendency. Galaxies are not frozen islands suspended in darkness. They travel through space while interacting gravitationally with neighboring galaxies. Entire groups move together. Clusters drift through larger environments. Streams of matter flow along cosmic filaments. Gravity constantly reshapes positions and motions over immense spans of time. Gravity serves as the primary architect of these changes. Every concentration of matter attracts surrounding matter. A slightly denser region pulls material inward. As more matter accumulates, gravitational attraction increases. Over billions of years, tiny differences present in the early universe grow into the enormous structures observed today. Yet gravity alone does not always create straight inward motion. Matter rarely falls perfectly toward a center. Small sideways motions almost always exist. A cloud may drift slightly to one side. A galaxy may approach another from an angle. A stream of gas may enter a region with a small offset. These tiny departures from perfect alignment become increasingly important as gravity gathers material together. Astronomers use a concept called angular momentum to describe rotational motion. Angular momentum represents the tendency of an object or system to continue rotating unless acted upon by external influences. The principle is familiar in everyday life. A spinning wheel tends to keep spinning. A rotating top maintains its motion for a time. In the cosmos, the same principle operates across scales far larger than anything encountered on Earth. When matter approaches a region from slightly different directions, angular momentum can emerge naturally. Even a very small sideways motion can become significant as gravity draws material inward. Over long periods, these subtle motions influence the development of larger structures. Rotation often begins not as a dramatic event, but as a gentle imbalance. Observations indicate that these imbalances are widespread throughout the universe. Perfect symmetry is rare. Matter does not arrange itself with flawless precision. Instead, countless small irregularities shape the paths followed by gas dust stars and galaxies. These irregularities create opportunities for angular momentum to appear. The observable universe therefore presents an interesting contrast. On the larger scales, no overall cosmic spin has been detected. Yet within the expanding cosmos, motion continuously generates conditions that favor rotation. Structures form from uneven distributions of matter. Gravity amplifies those uneven distributions. Sideways motions persist. Angular momentum develops and remains present. Modern surveys map millions of galaxies across enormous distances. These observations reveal a universe that evolves through motion and interaction. Galaxies merge, clusters grow, matter flows along filaments. Every process unfolds over timescales measured in millions or billions of years. Human lifetimes are far too short to witness most of these changes directly, but careful observation allows astronomers to reconstruct the story. The story begins with movement already present. Matter is never arranged with complete stillness. Even tiny differences in velocity influence future evolution. As gravity acts over immense spans of time, those small motions leave lasting effects. The universe becomes a place where rotation repeatedly emerges from ordinary physical processes. This pattern does not require special mechanisms unique to individual objects. Instead, it reflects general properties of matter and gravity. Whenever material gathers from different directions, slight imbalances can appear. Whenever such imbalances exist, angular momentum can arise. The result is a cosmos filled with structures that move in complex ways. The largest observable view therefore establishes a foundation for understanding why spin is so common. Rotation is not imposed from outside. It develops naturally within an expanding universe shaped by gravity motion and uneven distributions of matter. Observations indicate that these conditions have existed throughout cosmic history. Across enormous distances and immense spans of time, they help create a universe in which spinning motion appears again and again. The largest structures that can be studied in detail are not individual galaxies, but collections of galaxies bound together by gravity. These enormous systems occupy regions spanning millions of light-years and contain hundreds, sometimes thousands of galaxies moving through a shared gravitational environment. They represent some of the most massive structures that remain gravitationally connected in the observable universe. Within these immense gatherings, astronomers find another example of a surprising pattern. Rotation appears once again. Galaxy clusters seem tranquil when viewed through ordinary images. Their slow evolution unfolds across timescales so vast that no visible change occurs during a human lifetime. Yet measurements reveal continuous motion. Every galaxy within a cluster travels through space. Some move toward the center, others follow elongated paths around the cluster. Many experience repeated gravitational encounters with neighboring galaxies. The entire system remains active despite its calm appearance. For much of modern astronomy, galaxy clusters were viewed primarily as collections of objects moving in many directions, without any significant overall rotation. The motions appeared largely random. Individual galaxies raced through clusters at speeds reaching thousands of kilometers per second. Such complexity made it difficult to identify larger patterns. Early observations lacked the precision needed to detect subtle collective movement. As telescopes improved and surveys expanded, astronomers began gathering measurements from larger numbers of galaxies. Detailed maps of positions and velocities allowed researchers to examine clusters as complete systems rather than isolated objects. These studies revealed that some clusters exhibit signs of coherent rotation. The effect is generally slow compared with the rapid rotation observed inside many individual galaxies, but it appears measurable in certain cases. Observations indicate that not every cluster rotates in the same manner. Some show stronger evidence than others. In many cases, the signal remains weak and difficult to separate from other forms of motion. Scientists continue studying these systems because the measurements are challenging, and because cluster structures are often complicated by mergers and ongoing growth. Nevertheless, evidence suggests that rotation can emerge even on these enormous scales. The existence of cluster rotation raises an important question. How does such motion develop? The answer begins with the environment surrounding the clusters themselves. No galaxy cluster forms in complete isolation. Each grows within the larger network of the cosmic web. Vast filaments of matter connect clusters across immense distances. Along these filaments, galaxies' gas and dark matter flow gradually toward denser regions. The process unfolds over billions of years. Matter streams inward from multiple directions. These incoming flows are rarely perfectly balanced. One filament may contribute more material than another. Galaxies may arrive at slightly different angles. Groups of galaxies may enter a cluster while already moving together. Such asymmetries introduce sideways motion into the growing system. Gravity amplifies the consequences of these small differences. Material falling inward does not always travel directly toward the center. Instead, trajectories often curve because incoming matter possesses some degree of lateral motion. As more material accumulates, these motions combine and influence the developing cluster. Gradually, angular momentum can emerge on scales spanning millions of light-years. Computer simulations provide valuable insight into this process. Modern cosmological simulations begin with conditions resembling those inferred for the early universe. Researchers allow gravity to shape matter over billions of simulated years. The resulting structures display many features seen in real observations. Among these features are rotational motions developing within growing galaxy clusters. The simulations suggest that cluster spin can arise naturally from ordinary structure formation. The growth of clusters also involves repeated mergers. Smaller groups frequently collide and combine to form larger systems. These events are not sudden impacts in the everyday sense. Instead, they unfold over immense periods of time. Entire galaxies pass through one another with relatively little direct contact because the distances between stars are so great. Nevertheless, gravity strongly influences the motion of the merging systems. When two galaxy groups approach from slightly offset directions, they carry angular momentum into the merger. The combined structure may inherit part of that motion. Repeated mergers across billions of years contribute additional complexity. The resulting cluster can retain traces of the motions that helped build it. The space between galaxies within clusters contains enormous quantities of extremely hot gas. This gas reaches temperatures of many millions of degrees Celsius and emits powerful X-rays. Observatories designed to detect X-rays reveal the shape and movement of this material. Studies sometimes find patterns suggesting that the gas itself participates in large-scale rotational motion. These observations provide another line of evidence supporting the idea that some clusters possess measurable spin. Dark matter plays a central role as well. Although it cannot be observed directly, its gravitational influence dominates the mass of most galaxy clusters. Dark matter forms extensive halos surrounding visible galaxies and cluster structures. Simulations indicate that dark matter can acquire angular momentum through the same processes affecting ordinary matter. As the dark matter halo develops rotational characteristics, it influences the motions of galaxies and gas embedded within it. Scientists remain cautious when interpreting these findings. Measuring rotation across such enormous distances is difficult. Observational uncertainties remain significant in many cases. Some apparent rotational signals may arise from complex motions unrelated to true large-scale spin. Researchers continue refining techniques and collecting additional data to distinguish between these possibilities. Observations indicate rotation in certain clusters, while the full prevalence and strength of cluster spin remain active areas of investigation. Despite these uncertainties, a broader pattern becomes increasingly clear. Gravity does not merely gather matter into larger structures. The process of gathering often introduces angular momentum. Incoming material arrives from multiple directions. Slight imbalances persist. Mergers occur with imperfect alignment. Over immense spans of time, these conditions encourage rotational motion to emerge. Galaxy clusters therefore provide another example of a recurring cosmic tendency. Even on scales far beyond individual galaxies, nature rarely assembles structures through perfectly symmetrical collapse. Growth proceeds through uneven flows and gradual accumulation. Angular momentum appears as a natural consequence of those processes. Across regions spanning millions of light-years, the same underlying principles continue operating. Matter moves through the cosmic web. Gravity shapes its path. Small sideways motions survive and accumulate. Rotation develops within structures that seem unimaginably large. The pattern remains gentle, slow, and subtle, compared with many smaller astronomical systems, yet it reflects the same fundamental behavior. The universe continually transforms tiny imbalances into organized motion, creating spinning structures even among its largest gravitationally bound realms. Galaxies occupy a scale smaller than clusters, yet remain among the most magnificent structures in the observable universe. Each galaxy contains vast numbers of stars, immense clouds of gas and dust, and large quantities of dark matter. Some galaxies contain a few million stars, others contain hundreds of billions. They appear in many forms, but among all their differences, one characteristic stands out with remarkable consistency. Galaxies move, and many of them rotate. From a great distance, a spiral galaxy resembles a luminous whirlpool suspended in darkness. Bright arms curve outward from a central region. Stars and gas trace elegant patterns that seem almost motionless in photographs. Yet every part of the galaxy is in continuous motion. Stars orbit the galactic center. Gas clouds circle through the disk. Dust drifts along enormous pathways shaped by gravity. The entire structure turns slowly through space. The galaxy that contains Earth, the Milky Way, provides a familiar example. The solar system moves around the galactic center, along with billions of other stars. One complete orbit requires roughly 200 million years. Human history occupies only a tiny fraction of that interval. The motion is therefore impossible to perceive directly during a lifetime, yet precise measurements leave no doubt that it occurs. Astronomers determine galactic rotation through several methods. They observe how light changes as stars and gas move toward or away from Earth. Material approaching an observer produces a slight shift in wavelength, while material moving away produces a shift in the opposite direction. By measuring these differences across a galaxy, researchers construct maps showing how various regions move. These maps reveal organized rotation on an enormous scale. Spiral galaxies provide some of the clearest examples. Their disks rotate around a central region containing dense concentrations of stars. The motion is not rigid like the turning of a solid wheel. Instead, different regions travel at different speeds. Stars closer to the center generally complete orbits more quickly than stars farther away. The galaxy behaves as a vast gravitational system rather than a single solid object. Observations show that rotation plays a fundamental role in shaping spiral galaxies. Without angular momentum, material falling inward under gravity would tend to collapse into a more compact form. Rotation provides resistance to direct inward collapse. As gas and stars move around the center, their motion helps maintain the extended disk structure that characterizes many galaxies. The origin of this rotation traces back to the early stages of galactic formation. Billions of years ago, matter in the young universe was distributed unevenly. Slightly denser regions attracted surrounding material through gravity. As gas and dark matter flowed inward, perfect symmetry rarely existed. Matter arrived from different directions and with different velocities. Tiny sideways motions became important. As gravitational collapse continued, angular momentum accumulated. The growing protogalaxy, a developing galactic structure, inherited motion from the material entering it. The principle of angular momentum conservation ensured that this motion persisted. As matter concentrated into a smaller region, rotational effects became increasingly significant. The developing galaxy gradually acquired organized spin. Computer simulations reproduce this process with impressive accuracy. Starting from conditions consistent with observations of the early universe, researchers allow gravity to shape matter over billions of years. Rotating galaxies emerge naturally from these calculations. The simulations show that angular momentum develops through interactions between neighboring structures and through the uneven inflow of matter from the surrounding environment. Dark matter plays a major role in this evolution. Although invisible dark matter forms massive halos that surround galaxies, these halos contain most of a galaxy's mass. During formation, gravitational interactions between neighboring halos transfer angular momentum. The visible galaxy develops within this rotating gravitational framework. Stars and gas inherit motion influenced by the surrounding dark matter structure. Not all galaxies resemble spirals. Elliptical galaxies display a different appearance. Instead of flat disks and distinct arms, they often appear rounded or elongated. For many years, astronomers viewed ellipticals as systems dominated by random stellar motion rather than organized rotation. Modern observations reveal a more complex reality. Some elliptical galaxies rotate significantly, others rotate only modestly. In many cases, stars follow intricate orbital patterns that reflect a long history of mergers and gravitational interactions. Rotation remains present, though often less visually obvious than in a spiral galaxy. The details depend on how the galaxy formed and evolved across cosmic time. Galaxy mergers strongly influence rotational behavior. When galaxies approach one another, gravity alters their trajectories. Over long periods, they may combine into a larger system. These mergers redistribute stars' gas and angular momentum. A rotating spiral galaxy may merge with another galaxy and produce an elliptical remnant possessing a different pattern of motion. The resulting structure still reflects the influence of angular momentum even if the visible appearance changes dramatically. Irregular galaxies present another variation. These systems lack the clear structure of spirals and ellipticals. Many have experienced recent gravitational disturbances or interactions with neighboring galaxies. Their motions can appear chaotic, yet careful study often reveals underlying patterns of angular momentum inherited from their formation history and subsequent encounters. One of the most important discoveries in galactic astronomy emerges from measurements of rotation speed. Observations show that stars far from galactic centers often move faster than expected, based solely on visible matter. This finding provides strong evidence for dark matter. The additional gravitational influence supplied by dark matter helps explain why outer regions continue orbiting at observed speeds. The study of galactic rotation therefore contributes to understanding both visible and invisible components of the universe. Measurements of motion reveal information about mass structure and evolutionary history. Rotation becomes a powerful tool for exploring phenomena that cannot be observed directly. Across billions of galaxies scattered throughout the observable universe, the pattern repeats. Gravity gathers matter. Slight asymmetries introduce angular momentum. Conservation preserves that motion. Rotating structures emerge and persist across immense spans of time. Spiral disks turn gracefully. Elliptical systems retain complex motions. Irregular galaxies carry traces of rotational histories shaped by interaction and change. The prevalence of galactic rotation demonstrates that spin is not a rare feature produced under exceptional circumstances. Instead, it arises naturally during the formation of large cosmic structures. Wherever matter gathers unevenly under gravity, angular momentum tends to appear. Galaxies stand as some of the clearest and most beautiful expressions of that universal tendency, their slow turning preserving the history of motions that began billions of years ago. Beyond the visible stars, glowing gas, and dark lanes of dust that define a galaxy, lies a component that cannot be seen directly. It emits no light, reflects no light, and absorbs no light in any measurable way. Yet its gravitational influence shapes the structure and motion of galaxies throughout the universe. Astronomers call this unseen substance dark matter. Understanding galactic rotation requires understanding the role dark matter plays in guiding motion across enormous distances. When astronomers first began measuring the rotation of galaxies in detail, they expected to find a pattern similar to the motions observed within planetary systems. In a planetary system, most of the mass resides near the center. As distance from the center increases, orbital speeds generally decrease. The outer planets move more slowly than the inner planets because the central mass dominates the gravitational environment. A similar result seemed reasonable for galaxies. Much of the visible light comes from stars concentrated toward the central regions. If visible matter accounted for nearly all galactic mass stars far from the center, would be expected to orbit more slowly than stars closer in. Yet observations revealed something different. As measurements improved during the 20th century, astronomers examined the motions of stars and gas across galactic disks. Instead of declining sharply with distance rotation, speeds often remained surprisingly high. In many galaxies, stars located far from the center moved almost as rapidly as stars much closer to it. This pattern appeared repeatedly in galaxy after galaxy. The result created a puzzle. Visible matter alone could not easily explain the observed motions. Additional mass appeared necessary. Something unseen seemed to contribute gravitational influence throughout the galaxy. The concept of dark matter emerged as the leading explanation. Modern observations strongly support this interpretation. Galaxies appear embedded within enormous dark matter halos extending far beyond the visible regions. These halos contain far more mass than the stars and gas that can be directly observed. Their gravitational influence shapes how galaxies rotate and evolve. Dark matter affects galactic spin in two important ways. First, it helps determine the rotational speeds observed today. Second, it plays a critical role during galaxy formation itself. Long before stars filled a galaxy with light, dark matter structures were already influencing the motions of ordinary matter. Current cosmological models suggest that dark matter began forming gravitational concentrations early in cosmic history. Small density differences grew over time as gravity attracted additional material. These concentrations developed into halos that served as gravitational foundations for future galaxies. Ordinary matter flowed into these regions, eventually cooling and forming stars. The process was not perfectly symmetrical. Dark matter halos interacted with neighboring structures. Gravitational forces exerted subtle torques, a torque being an influence that changes rotational motion. Through these interactions, halos acquired angular momentum. Computer simulations indicate that this mechanism naturally generates spin during structure formation. As gas fell into rotating dark matter halos, it inherited part of the existing motion. Conservation of angular momentum ensured that the incoming material continued rotating as it collapsed. Over time, the gas flattened into rotating disks. Stars formed within those disks and preserved the rotational patterns established during the galaxy's early history. Observations and simulations together suggest that dark matter does not merely support galactic rotation after formation. It helps create the conditions that allow organized rotation to develop in the first place. The visible galaxy grows within a larger invisible structure whose gravitational influence guides the movement of matter. Researchers study this process using powerful computer models capable of simulating billions of years of cosmic evolution. These simulations begin with conditions consistent with observations of the early universe. Gravity acts upon both ordinary matter and dark matter. Gradually, halos form, merge, and grow. Gas flows inward. Galaxies emerge. One striking result appears repeatedly. Rotating galaxies develop naturally. The simulations do not require special instructions to produce spin. Angular momentum arises because matter enters growing structures unevenly. Dark matter halos participate in these interactions, acquiring rotational characteristics that influence everything forming within them. The details remain complex. Dark matter has never been detected directly despite extensive efforts. Scientists know of its existence through gravitational effects rather than direct observation. Measurements involving galactic rotation, galaxy clusters, gravitational lensing, and large-scale structure all support the conclusion that substantial unseen mass exists. Yet the fundamental nature of dark matter remains uncertain. Observations indicate how dark matter behaves gravitationally. It remains uncertain precisely what particle or particles compose it. Numerous possibilities have been proposed and investigated. Experiments continue searching for direct evidence. For now, the exact identity of dark matter remains one of the major unanswered questions in modern physics. Despite that uncertainty, its influence on galactic motion is well established. The rotational behavior of galaxies provides some of the strongest evidence for its existence. Without dark matter, many observed rotation patterns become difficult to explain. With dark matter included, theoretical models align much more closely with observations. The relationship between visible matter and dark matter reveals another aspect of why rotation appears so frequently throughout the universe. Gravity acts on all mass, regardless of whether that mass emits light. Visible matter represents only part of the cosmic inventory. Invisible mass contributes to the same gravitational processes that generate angular momentum. As galaxies grow, dark matter and ordinary matter become partners in structure formation. Their motions intertwine through gravity. Angular momentum develops within the combined system. The resulting galaxy carries rotational characteristics inherited from a long history of interactions, inflows, and gravitational influences extending far beyond what telescopes can directly see. Viewed from a distance, a rotating galaxy appears serene. Its stars trace elegant paths around a luminous center. Beneath that calm appearance lies a much larger structure dominated by invisible matter. The motion of countless stars reflects the gravitational architecture of a halo extending far into surrounding space. Dark matter therefore deepens the story of cosmic spin. Rotation does not arise solely from the visible portions of galaxies. It emerges within larger gravitational environments shaped largely by unseen mass. The universe reveals that even invisible structures participate in the processes that generate angular momentum. Through their influence, galaxies become enduring examples of how gravity transforms tiny asymmetries into organized rotational motion across cosmic scales. Between the bright stars that illuminate a galaxy lies a vast realm of gas and dust. At first glance, these regions may appear empty. Through ordinary telescopes, much of the space separating stars seems dark and featureless. Yet detailed observations reveal a rich environment filled with material drifting through the galaxy. This interstellar medium, the matter existing between stars, plays a central role in the story of cosmic rotation. The interstellar medium consists primarily of hydrogen gas, accompanied by smaller amounts of helium and traces of heavier elements. Tiny dust grains composed of materials such as carbon and silicates drift among the gas. Although the density is extraordinarily low compared with conditions on Earth, the sheer size of these regions means that enormous quantities of matter are present. This material does not remain motionless. Gas flows through the galaxy under the influence of gravity, radiation, magnetic fields, and the motion of nearby stars. Vast streams of matter move across distances measured in light years. Clouds form, evolve, and disperse. Everywhere within the interstellar medium, movement persists. Among the most important structures are giant molecular clouds. These enormous accumulations of gas and dust represent some of the coldest and densest regions within galaxies. Individual clouds may contain enough material to create thousands or even millions of stars. They occupy regions spanning tens or hundreds of light years and serve as the primary nurseries of stellar formation. Observations show that these clouds frequently rotate. The rotation is often slow and subtle. A molecular cloud does not spin like a solid object. Different regions move at different speeds. Turbulence, a state of irregular fluid motion, creates additional complexity. Nevertheless, measurements reveal organized angular momentum within many clouds. The material possesses a preferred direction of motion rather than complete randomness. Astronomers detect this rotation by studying the light emitted or absorbed by molecules inside the clouds. Different regions move toward or away from Earth at slightly different speeds. Careful analysis allows researchers to map these motions and identify rotational patterns. The results demonstrate that angular momentum exists long before individual stars begin to form. The origin of cloud rotation reflects the broader motions occurring throughout the galaxy. Molecular clouds do not appear suddenly from nothing. They emerge from gas already moving through a rotating galactic environment. The Milky Way itself rotates, carrying stars, gas, and dust around its centre. Within this larger motion, local disturbances create regions where material accumulates. As gas streams through the galaxy, gravitational forces compress certain areas. Shock waves from stellar explosions may squeeze nearby material. Encounters between clouds alter trajectories. Magnetic fields influence charged particles. These processes gather matter into denser concentrations. During accumulation, perfect symmetry remains rare. Gas enters forming clouds from different directions and with slightly different velocities. Some material approaches more directly, some arrives with sideways motion. Small imbalances emerge naturally. As gravity strengthens within the growing cloud, these differences contribute angular momentum to the developing structure. The process resembles a recurring theme already visible on larger scales. Whether examining clusters, galaxies, or clouds, matter rarely converges with perfect alignment. Tiny offsets appear almost everywhere. Gravity amplifies their consequences. Rotation develops gradually from these small departures from symmetry. Within molecular clouds, another important phenomenon appears. Observations reveal turbulent motion throughout the gas. Rather than flowing smoothly, the material forms swirling patterns across many scales. Large currents break into smaller currents. Regions interact in complex ways. The cloud resembles a dynamic fluid environment rather than a quiet accumulation of matter. Turbulence influences the distribution of angular momentum. Some regions gain rotational motion while others lose it. Small rotating structures emerge inside larger rotating structures. The cloud becomes a hierarchy of motions nested within one another. Despite this complexity, the overall cloud often retains a measurable sense of rotation. Computer simulations help researchers understand these behaviors. By modeling gravity, gas dynamics, magnetic fields, and turbulence, scientists can recreate many observed features of molecular clouds. The simulations consistently show angular momentum arising naturally as matter gathers. Rotational motion becomes an expected outcome of cloud formation rather than an unusual exception. The influence of magnetic fields adds another layer to the story. Interstellar space contains weak magnetic fields extending across large distances. Although extremely faint compared with magnets used on Earth, these fields can affect the motion of ionized gas over vast scales. Magnetic forces help redistribute angular momentum within clouds and influence how material moves during collapse. Researchers continue studying the exact balance between gravity, turbulence, and magnetic effects. Observations indicate that all three contribute to cloud evolution. It remains uncertain how strongly each factor dominates under different conditions. The relative importance varies from cloud to cloud, yet all evidence points toward a dynamic environment where motion remains fundamental. The rotational characteristics of molecular clouds are especially significant because these clouds represent the immediate environments from which stars eventually emerge. Before any star shines, before any planetary system exists, angular momentum is already present within the parent cloud. The future development of stellar systems begins within matter that is already moving. Different clouds display different rotational strengths. Some rotate more rapidly than others. Some contain more turbulence. Some possess stronger magnetic influences. Their histories differ depending on location and past interactions. Despite this variety, the overall pattern remains remarkably consistent. Angular momentum appears again and again. The interstellar medium therefore reveals another stage in the progression of cosmic spin. Rotation is not confined to large structures such as galaxies. It exists within the raw material from which future astronomical objects will form. Clouds drifting between the stars carry motions inherited from their surroundings and shaped by their own evolution. Across the dark spaces of a galaxy, enormous reservoirs of gas and dust slowly shift under gravity. Streams converge, matter accumulates, tiny asymmetries persist, turbulence stirs the material, magnetic fields guide its motion. Through these ordinary physical processes, angular momentum becomes woven into the structure of the clouds themselves. The result is a galaxy filled not only with rotating stars and rotating disks, but also with rotating reservoirs of future stars. Even before the next generation of luminous objects exists, the tendency towards spin is already present within the cold clouds, scattered among the stars, quietly preserving motion across immense spans of space and time. Within the cold depths of giant molecular clouds, gravity slowly begins to gain influence over certain regions. Small concentrations of gas and dust become slightly denser than their surroundings. These denser pockets attract additional material. As more matter gathers, gravitational attraction strengthens further. Over long periods, a process of collapse begins. From these collapsing regions, stars emerge. The birth of a star is one of the clearest demonstrations of how angular momentum shapes the universe. Long before nuclear fusion ignites in a stellar core, the future star inherits motion from the cloud that surrounds it. The cloud may rotate only slowly. Its angular momentum may be distributed across an enormous volume. Yet as gravity pulls material inward, the consequences of that rotation become increasingly important. A collapsing cloud does not simply shrink evenly in every direction. Even an extremely small amount of rotational motion influences the process. As gas falls inward, conservation of angular momentum becomes more apparent. The same physical principle observed throughout the cosmos operates here as well. Angular momentum tends to remain constant unless external influences remove it. An everyday example helps illustrate the idea. A rotating skater spins faster when drawing arms closer to the body. The total angular momentum remains nearly unchanged, but the rotation rate increases because the mass occupies a smaller region. Although a forming star differs greatly from a skater, the underlying principle remains the same. As a cloud contracts under gravity, its size decreases dramatically. Material that once occupied a vast region becomes concentrated into a much smaller volume. Because angular momentum is largely conserved, rotational speed increases. A slowly rotating cloud can therefore produce a rapidly rotating stellar system. Observations confirm this behavior. Regions where stars form often contain rotating structures surrounding young stellar objects. Astronomers detect flattened disks of gas and dust encircling newly forming stars. These disks arise because rotation prevents all material from falling directly into the center. Gravity constantly pulls inward. Rotation provides a competing influence. Material moving sideways continues its motion, while simultaneously being drawn inward. The result is the formation of a rotating disk around the developing star. Gas spirals gradually through the disk while angular momentum is redistributed among different regions. The central object known as a protostar during this stage continues growing as additional matter falls inward. Temperatures rise steadily. Gravitational energy transforms into heat. The surrounding disk rotates around the protostar while supplying fresh material to the center. Without angular momentum, the process would look very different. Matter would collapse almost directly inward, producing a more spherical structure with far less organization. Instead, rotation naturally creates flattened systems. The disk becomes one of the defining features of stellar birth. Astronomers observe these disks throughout the Milky Way and other galaxies. Powerful radio telescopes and infrared observatories penetrate the dust that obscures visible light. These instruments reveal rotating disks around stars at many stages of development. The observations align closely with theoretical models describing how angular momentum influences collapse. The amount of angular momentum present in a molecular cloud creates an interesting challenge. If all of the cloud's angular momentum remained concentrated in the newborn star, the star could rotate so rapidly that stable formation would become difficult. Nature solves this problem through several mechanisms that redistribute angular momentum during collapse. Part of the angular momentum remains within the surrounding disk. Some transfers outward through interactions between different regions of gas. Magnetic fields also help carry angular momentum away from the center. These processes allow material to continue falling inward while preventing excessive rotational speeds. Young stars often produce powerful outflows of gas as well. Narrow jets emerge from regions near the protostar and extend across enormous distances. These jets help remove angular momentum from the system. By carrying motion away from the center, they permit additional material to accrete onto the growing star. Observations indicate that jets are common during stellar formation. Their presence suggests that angular momentum removal is not a minor detail, but a fundamental aspect of how stars are born. The universe repeatedly develops methods for redistributing rotational motion while preserving the overall principle of angular momentum conservation. As collapse continues, the central protostar grows denser and hotter. Eventually, temperatures become high enough for nuclear fusion to begin. Hydrogen nuclei start combining to form helium. A true star comes into existence. Yet even at this moment, the influence of angular momentum remains evident. The newborn star rotates. Some stars rotate relatively slowly. Others rotate much more rapidly. The exact rate depends on factors including mass magnetic activity, formation history, and interactions with surrounding material. Regardless of the details, rotation appears as a nearly universal characteristic of stellar birth. Observations across the galaxy reveal young stars spinning at a wide range of speeds. Certain massive stars complete rotations in less than a day. Others require longer periods. The diversity is considerable, but the presence of rotation itself is remarkably consistent. Computer simulations reproduce these outcomes. Starting with realistic molecular clouds containing modest angular momentum, researchers observe the formation of rotating disks and rotating protostars. The simulations demonstrate that spin emerges naturally from the collapse process. No special conditions are required beyond the ordinary asymmetries already present within the cloud. The birth of a star therefore represents another step in the inward progression of cosmic rotation. Angular momentum begins within large-scale galactic environments. It appears within interstellar clouds. It survives the collapse of those clouds. As gravity concentrates matter into increasingly smaller regions, rotational effect becomes stronger and more visible. A star does not acquire spin through a separate mechanism introduced late in its development. Rotation is inherited. The motion carried by diffuse gas across distances of many light years persists through collapse and becomes concentrated within a newly formed stellar object. The star emerges already turning. Throughout the Milky Way, countless stellar nurseries continue this process. Cold clouds collapse, disks form, protostars grow, jets carry away excess angular momentum, nuclear fusion ignites, new stars begin their long lives. In each case, the same underlying principle remains present. The conservation of angular momentum transforms gentle motions within enormous clouds into the rotation of individual stars, revealing once again how deeply spin is woven into the structure of the universe. A star begins its life rotating, but its rotation does not remain unchanged. From the moment nuclear fusion ignites in the core, a long process of evolution begins. Over millions and billions of years, the star continues interacting with its surroundings, redistributing energy, losing material, and responding to internal forces. Throughout these changes, angular momentum remains an important influence. The rotation observed in a mature star reflects not only its birth, but also the history of its entire life. The Sun provides a familiar example. Careful observations show that the Sun rotates continuously. Dark regions known as sunspots move across its visible surface, allowing astronomers to measure the rate of rotation. The Sun does not behave like a rigid solid object. Instead, different regions rotate at different speeds. Near the equator, rotation occurs more rapidly than near the poles. This behavior is called differential rotation. Because a star consists primarily of hot plasma, rather than solid material, various layers can move independently. The outer regions are free to flow in complex patterns shaped by gravity-magnetic fields, pressure and internal motion. Differential rotation becomes a common feature among many stars. The presence of differential rotation influences stellar magnetic fields. Motion within the conducting plasma generates magnetic activity through a process known as the stellar dynamo. In simple terms, the movement of electrically charged particles helps create and sustain magnetic fields. Rotation therefore affects much more than the motion of the star itself. It also influences magnetic behavior surface activity and the release of energetic particles into surrounding space. Young stars often rotate more rapidly than older stars. This pattern appears repeatedly in astronomical observations. Newly formed stars inherit significant angular momentum from their birth environments. Over time, however, many gradually lose rotational speed. One important mechanism involves stellar winds. A stellar wind is a continuous outflow of particles escaping from the star into space. The Sun produces such a wind today. Although individual particles carry little mass, the cumulative effect over immense spans of time becomes significant. Magnetic fields connect the stellar wind to the rotating star. As particles stream outward, they carry angular momentum away with them. The process acts like a subtle brake. Rotation slows gradually as angular momentum leaves the system. For stars similar to the Sun, this slowing occurs over billions of years. Astronomers use this relationship as a tool for estimating stellar ages. Because many stars spin more slowly as they grow older, rotational measurements can provide clues about how long a star has existed. The method is not perfect, and many factors influence rotation rates, but it offers valuable insight into stellar evolution. Mass plays a major role in determining rotational behavior. Massive stars often rotate differently from smaller stars. Some very massive stars spin at extraordinary speeds. Their rapid rotation influences internal structure, surface shape, and the transport of material within the star. A rapidly rotating star may become slightly flattened. Instead of forming a perfect sphere, centrifugal effects cause the equatorial region to bulge outward. The difference is usually modest, but in extreme cases it becomes measurable. The star remains bound together by gravity, yet rotation alters its geometry. Rotation also affects how material moves inside a star. Hot plasma circulates through various layers, transporting energy and chemical elements. Faster rotation can enhance mixing processes. Material from deeper regions may reach the surface more efficiently. These changes influence stellar evolution and affect the composition observed by astronomers. Binary star systems introduce additional complexity. Many stars exist not alone but as members of pairs. Two stars orbit a common center of mass while simultaneously rotating on their own axes. Gravitational interactions between the companions can alter rotational behavior significantly. Tidal forces play a major role in such systems. Gravity raises distortions within each star somewhat analogous to ocean tides on Earth. Over long periods, these distortions exchange angular momentum between rotation and orbital motion. The process often drives the stars towards synchronized behavior. In certain binary systems, rotation becomes faster rather than slower. Material may flow from one star to another. The receiving star gains both mass and angular momentum. Such interactions can produce unusually rapid rotation and dramatically alter the future evolution of the system. Observations reveal an extraordinary range of stellar rotation rates throughout the galaxy. Some stars rotate once every few hours, others require months or even longer. This diversity reflects differences in mass-age magnetic activity formation history and interactions with companions. Despite these variations, one theme remains consistent. Rotation rarely disappears completely. Even after billions of years, stars generally retain at least some fraction of the angular momentum inherited during formation. The original motion may be modified, redistributed, or reduced, but it remains present. Astronomers study stellar rotation using multiple techniques. Surface features reveal rotational periods. Spectroscopic measurements detect motion through shifts in light. Space telescopes monitor subtle variations in brightness caused by rotating star spots. Together, these observations provide detailed information about how stars spin and evolve. Computer models help explain the patterns seen in real stars. Simulations incorporate gravity plasma physics, magnetic fields, and angular momentum transport. The results reproduce many observed behaviors, including rotational slowing, differential rotation, and the effects of binary interactions. These models show that rotation is deeply integrated into stellar physics rather than serving as a minor detail. The life of a star therefore becomes a long story of changing angular momentum. Rotation begins during gravitational collapse. It influences magnetic activity and internal structure. Stellar winds gradually remove motion. Companions may exchange angular momentum through tides and mass transfer. Throughout all these processes, the star remains a rotating object responding to the same physical principles that shape structures across the universe. From the perspective of cosmic history, a star preserves motion, inherited from much larger environments. The angular momentum, once distributed through an immense molecular cloud, becomes concentrated within a luminous sphere of plasma. Over billions of years, that motion evolves but endures. Every rotating star stands as evidence that the tendency towards spin survives not only through formation, but throughout the long and changing lives of the stars themselves. Around many young stars, the rotating disks that appear during stellar birth do not vanish immediately after the star forms. Instead, they persist for millions of years as vast, flattened structures composed of gas dust, ice, and microscopic particles. These disks represent one of the most important environments in astronomy because they give rise to planetary systems. Within them, the story of cosmic rotation continues in a new form. A newly formed star occupies the center of the system. Around it stretches a broad rotating disk, often extending billions of kilometers into space. The disk contains material left over from the stellar formation process. Although the central star now shines through nuclear fusion, much of the original cloud has not yet become part of the star itself. This remaining matter continues orbiting because of its angular momentum. Observations of young stars throughout the Milky Way reveal such disks in large numbers. Modern telescopes operating at radio and infrared wavelengths can image these structures directly. Some disks display rings, gaps, spirals, and other patterns created by ongoing physical processes. These observations provide valuable evidence that planetary systems emerge naturally from rotating environments. The motion within a protoplanetary disk, a disk where planets are forming, is highly organized. Material does not rotate as a rigid solid. Instead, regions closer to the star complete orbits more quickly than regions farther away. Gravity from the central star controls much of this movement. The result is a broad rotating structure in which every particle follows its own path around the center. Within the disk, countless dust grains collide gently. Some collisions cause particles to stick together. Over time, larger aggregates form. Millimeter-sized grains become centimeter-sized clumps. Those clumps may eventually grow into larger bodies. The process unfolds gradually across immense spans of time. Angular momentum plays a central role throughout this evolution. Material cannot simply fall directly into the star because it continues moving sideways along its orbit. Gravity constantly pulls inward, yet orbital motion keeps the material circulating around the center. The balance between these influences allows the disk to persist long enough for planet formation to occur. As particles grow larger, gravitational effects become increasingly important. Small bodies begin attracting nearby material. Regions of enhanced density develop. Over millions of years, these concentrations can evolve into planetesimals, the building blocks of planets. Some eventually become full-size planets, while others remain smaller objects. The emerging planetary system inherits the rotational characteristics of the original disk. Because the disk rotates in a particular direction, most planets form with orbital motions aligned to that same direction. Observations across the solar system illustrate this pattern clearly. The planets orbit the Sun in nearly the same plane and generally move in the same direction. This arrangement reflects their common origin within a rotating disk. The orderly architecture of planetary systems is therefore another consequence of angular momentum conservation. Motion inherited from the parent molecular cloud survives through stellar formation and remains visible in the orbits of planets. Not every planetary system develops identically. Observations of planets around other stars reveal tremendous diversity. Some planets orbit extremely close to their stars. Others travel along highly elongated paths. Giant planets may occupy locations very different from those found in the solar system. Yet despite these variations, the underlying influence of angular momentum remains evident. Computer simulations show that planetary systems evolve through numerous interactions. Young planets can exchange angular momentum with the surrounding disk. They may migrate inward or outward over time. Gravitational encounters between planets can alter orbital paths. Some objects may even be ejected entirely from the system. Throughout these changes, angular momentum remains conserved within the broader system, even as it shifts between individual components. The disk itself gradually changes as evolution proceeds. Material falls onto the central star. Some becomes incorporated into planets and smaller bodies. Stellar radiation and stellar winds remove gas from outer regions. Over millions of years, the once massive disk becomes thinner and less substantial. Eventually, most of the gas disappears. What remains is a mature planetary system containing planets, moons, asteroids, comets, and smaller debris. Although the disk has largely vanished, its rotational history remains preserved in the motions of these surviving objects. Astronomers observe young planetary systems at many stages of development. Some disks are only a few 100,000 years old. Others are several million years old and already show evidence of forming planets. By comparing these systems, researchers reconstruct the sequence through which planetary architectures emerge from rotating disks. One remarkable conclusion arises repeatedly. Planetary systems do not require unusual circumstances to form. The same physical principles appear across many regions of the galaxy. Gravity gathers material. Angular momentum prevents direct collapse. Rotating disks emerge naturally. Within those disks, planets develop. This realization has transformed modern astronomy. Planets were once thought to be relatively uncommon. Today, observations indicate that planetary systems are widespread throughout the Milky Way. Many stars possess planets. Many of those planets likely formed within rotating disks similar to the one that produced the solar system. The prevalence of planetary systems reinforces a broader theme visible throughout the universe. Rotation is not confined to galaxies or stars. It remains present within the environments where entirely new classes of objects arise. The same angular momentum that shaped a molecular cloud and guided stellar birth continues influencing the assembly of planetary worlds. Every orbiting planet therefore carries a record of earlier motions. Its path around a star reflects angular momentum inherited through a chain of events stretching back to the parent cloud from which the system formed. The planet's existence depends upon the persistence of rotational motion across multiple stages of cosmic evolution. Within the quiet disks surrounding young stars, matter slowly organizes itself into future worlds. Dust becomes rock, gas gathers into giant planets, orbits emerge from rotational order. Over immense spans of time, the rotating disk transforms into a planetary system. Through this process, angular momentum continues its journey inward, shaping the environments that will eventually contain planets, moons, and the countless smaller bodies that accompany them. Within a mature planetary system, rotation appears in forms both familiar and subtle. Planets orbit their stars, moons orbit planets. Yet another type of motion exists alongside these orbital paths. Many worlds also rotate around their own axes. Day and night arise from this turning motion. Across the solar system and throughout the growing catalogue of planets discovered around other stars, axial rotation proves to be one of the most widespread characteristics of planetary bodies. Earth rotates once approximately every 24 hours. This steady motion produces the daily cycle of sunlight and darkness experienced across the planet. Although the rotation feels imperceptible to those standing on the surface, every location moves through space continuously as the planet turns. At the equator, the rotational speed reaches more than 1,000 kilometers per hour. Earth is not unusual in possessing spin. Nearly every major body in the solar system rotates. Some turn slowly, others rotate rapidly. The differences reveal much about their histories and the processes that shaped them. Among the planets, Jupiter provides one of the most striking examples. Despite its enormous size, it completes a rotation in less than 10 hours. This rapid spin causes the giant planet to bulge noticeably at its equator. The planet is not perfectly spherical, because centrifugal effects slightly oppose gravity in the equatorial region. Jupiter's rotation also influences its atmospheric structure, helping create the alternating bands and long-lived storms visible through telescopes. Saturn displays a similar pattern. Its rapid rotation contributes to an even more pronounced equatorial bulge. Uranus and Neptune also rotate relatively quickly. Across the giant planet's spin strongly affects atmospheric circulation, magnetic fields, and internal dynamics. The rocky planets exhibit greater variety. Mars rotates at a rate similar to Earth's. Mercury turns much more slowly. Venus presents one of the most unusual cases. It rotates very slowly and in a direction opposite to that of most planets in the solar system. This retrograde rotation means that the planet spins in the reverse direction compared with its orbital motion. The existence of such differences demonstrates that planetary rotation evolves over time. A planet does not necessarily preserve its original spin unchanged from formation. Impacts, gravitational interactions, and tidal forces can modify rotational behavior across billions of years. The origin of planetary spin begins during formation within the rotating protoplanetary disk. As growing bodies accumulate material, they inherit angular momentum from the surrounding environment. Collisions between planetesimals contribute additional motion. The resulting planet emerges with a particular rotational state determined by countless interactions during its assembly. Large impacts can dramatically alter that state. During the early history of the solar system, collisions between planetary bodies occurred frequently. Some impacts were gentle by astronomical standards. Others were immense events involving objects hundreds or thousands of kilometers across. Such collisions transfer angular momentum. A sufficiently large impact can accelerate rotation, slow it, or even change the orientation of the rotational axis. Current models suggest that Earth's moon formed after a giant impact early in Earth's history. If this interpretation is correct, the event would have significantly influenced the rotational characteristics of both Earth and the material that eventually became the moon. Axial tilt represents another consequence of these processes. Earth's rotational axis is inclined relative to its orbital plane. This tilt creates the seasons. Other planets possess different tilts, some modest and some extreme. Uranus rotates with an axis tilted so dramatically that it effectively spins on its side compared with most other planets. Observations indicate that large collisions during formation may explain such unusual orientations. Moons also participate in the story of rotation. Many moons rotate while orbiting their parent planets. A particularly common outcome is tidal locking. In a tidally locked system, the same side of a moon always faces the planet it orbits. Earth's moon provides the most familiar example. The moon rotates around its axis, but it does so at exactly the rate required to keep one hemisphere facing Earth. This configuration results from tidal forces operating over long periods. Gravity creates slight distortions within the moon. These distortions gradually alter rotation until a stable arrangement emerges. Tidal locking appears throughout the solar system. Numerous moons orbiting the giant planets display the same behavior. Observations of planets around other stars suggest that tidal locking may also affect many exoplanets, especially those orbiting close to small stars. Tidal forces influence planetary rotation as well. Earth's rotation gradually slows because of interactions with the moon. The effect is extremely small on human timescales, but measurable through precise observations. Over millions of years, the length of a day changes slowly as angular momentum transfers between Earth's rotation and the moon's orbit. These processes reveal that angular momentum does not remain fixed within individual objects. Instead, it moves between components of a system, while the total amount remains conserved. Rotation, orbital motion, and tidal interactions become interconnected parts of a larger dynamical structure. Astronomers have now discovered thousands of exoplanets orbiting distant stars. Measurements increasingly provide information about their rotational properties. Although obtaining such data remains challenging, observations indicate that planetary spin is common beyond the solar system as well. Diverse worlds exhibit diverse rotational states shaped by formation histories and long-term evolution. Some exoplanets likely rotate rapidly. Others may be tidally locked. Some may possess axial tilts very different from those found in the solar system. Yet all reflect the influence of the same physical principles operating throughout the cosmos. The widespread presence of planetary rotation demonstrates how deeply angular momentum becomes embedded within the formation of worlds. A rotating molecular cloud produces a rotating disk. A rotating disk gives rise to planets. Those planets inherit motion and continue evolving through collisions and gravitational interactions. The resulting diversity is immense, but rotation remains a nearly universal feature. Across planetary systems scattered throughout the galaxy, worlds turn steadily through space. Some spin quickly, some rotate slowly, some possess unusual orientations, some have become tidally locked to nearby companions. Beneath these differences lies a common origin. Each rotating world preserves a portion of the angular momentum carried through countless stages of cosmic evolution, linking the motion of a planet to events that began long before the planet itself existed. Beyond the major planets and their large moons lies a vast population of smaller bodies. These objects may appear insignificant compared with stars, galaxies, or giant planets, Yet they provide some of the clearest evidence that rotation permeates every level of cosmic structure. Asteroids, comets, dwarf planets, and planetary rings all display motion shaped by angular momentum. Even among the smallest worlds, spin remains a defining characteristic. The asteroid belt between Mars and Jupiter contains millions of rocky bodies. Most are relatively small, though a few are large enough to be considered dwarf planets. Observations show that nearly all asteroids rotate. Some complete a rotation in a matter of hours. Others require days. Their shapes, compositions, and histories influence their rotational behavior. Unlike large planets, many asteroids possess irregular forms. Gravity is often too weak to pull them into spherical shapes. As a result, their rotation can produce dramatic changes in brightness when viewed from Earth. As an asteroid turns, different portions of its surface reflect sunlight toward observers. Astronomers use these variations to measure rotational periods. The rotational histories of asteroids are often linked to collisions. Throughout the early solar system, impacts occurred frequently. Many asteroids are fragments of larger bodies shattered by ancient collisions. When an impact breaks apart a parent object, the fragments inherit angular momentum from the event. Each piece may emerge spinning at a different rate. Even today, collisions continue occasionally. Although the asteroid belt is far less crowded than often imagined, encounters still occur over long timescales. These impacts alter rotational states and contribute to the diversity observed among asteroid populations. Sunlight itself can influence asteroid rotation. This effect, known as the Yarkovsky-O'Keefe-Radzievsky-Paddock effect, arises because absorbed sunlight is later emitted as heat. The resulting radiation carries momentum. Over millions of years, this tiny force can gradually change the rotation of small bodies. Some asteroids spin faster, others slow down. In certain cases, the effect becomes strong enough to alter an asteroid's shape or even break it apart. The existence of such a subtle mechanism illustrates how sensitive rotational motion can be. Even weak influences accumulate when given sufficient time. Across millions of years, tiny forces can produce measurable changes. Dwarf planets also display diverse rotational characteristics. Pluto rotates once every several Earth days. Other dwarf planets possess different periods and orientations. Many inhabit the distant regions beyond Neptune where sunlight is faint and temperatures are extremely low. Despite their remoteness, these worlds preserve evidence of the same physical principles that shape larger planets. Pluto presents an especially interesting case because of its relationship with its large moon, Charon. The two bodies are tidally locked to one another. Each always shows the same face to the other. Their mutual gravitational interaction has redistributed angular momentum until a stable configuration emerged. This arrangement demonstrates once again how rotation and orbital motion exchange angular momentum across time. Comets provide another perspective on rotational behavior. These icy bodies spend much of their existence in the outer solar system. When a comet approaches the Sun, solar heating causes gases to escape from its surface. Jets of gas and dust erupt into space, creating the familiar tails visible from Earth. These jets can influence rotation directly. Gas escaping from one region acts like a small thruster. Over time, repeated outflows alter the comet's spin. Observations reveal that some comets change rotational periods as they travel through the inner solar system. Others exhibit complex rotational states involving motion around multiple axes. The study of comet rotation offers insight into how even small bodies respond to ongoing physical processes. Rotation is not merely a relic of formation. It continues evolving through interactions with the surrounding environment. Among the most visually striking structures in planetary systems are rings. Saturn's rings provide the most famous example, though rings also surround Jupiter, Uranus, and Neptune. These magnificent formations consist of countless particles ranging from microscopic dust grains to chunks of ice many meters across. At first glance, a ring appears to be a single object. In reality, it is an immense collection of individual particles orbiting a planet. Each particle follows its own path under gravity. Regions closer to the planet move more rapidly than regions farther away. The ring therefore behaves as a rotating system composed of innumerable components. Angular momentum governs every aspect of ring dynamics. Collisions between particles redistribute energy and momentum. Gravitational interactions with moons create gaps and waves. The structure evolves continuously, while preserving the fundamental influence of rotational motion. Spacecraft observations reveal extraordinary detail within planetary rings. Narrow ringlets, spiral density waves, and complex patterns emerge from the interactions of countless orbiting particles. These structures demonstrate how angular momentum shapes behavior even among objects far smaller than planets. Researchers also observe disks and rings around dwarf planets, asteroids, and other small bodies. Such discoveries suggest that rotational processes operate across a broader range of environments than once imagined. Wherever matter gathers and moves under gravity, angular momentum leaves its mark. The smaller members of planetary systems therefore extend the story of cosmic spin into increasingly detailed territory. Large planets rotate, moons rotate, asteroids rotate, comets rotate. Rings revolve through intricate orbital patterns. Every scale reveals the same underlying tendency. What appears remarkable is not that some small bodies spin, but that so many do. Rotation emerges again and again because angular momentum accompanies matter throughout its history. From the earlier stages of cloud collapse to the formation of planets and the evolution of minor bodies, motion persists. Across the solar system and countless other planetary systems scattered throughout the galaxy, small worlds continue turning through space. Their rotations record ancient collisions, tidal interactions, solar influences, and formation histories. Each object preserves part of a larger narrative in which angular momentum flows through every level of cosmic structure. Even among the smallest bodies orbiting distant stars, the universe continues to express its enduring preference for spin. When a star approaches the end of its life, gravity and angular momentum begin interacting under increasingly extreme conditions. The familiar balance that allows a star to shine steadily for millions or billions of years eventually changes. Nuclear fusion alters the chemical composition of the stellar interior. Fuel becomes depleted. Internal pressure evolves. In some cases, the star leaves behind a compact remnant far denser than anything found among ordinary planets or living stars. Within these remnants, rotation reaches some of the most remarkable forms observed in nature. One outcome of stellar evolution is the formation of a white dwarf. A white dwarf emerges when a star with a mass broadly similar to that of the Sun exhausts its nuclear fuel and sheds its outer layers. The remaining core survives as an object roughly comparable in size to Earth, but containing a large fraction of the original stellar mass. The transformation dramatically reduces the size of the star. During this contraction, angular momentum conservation becomes increasingly important. The same principle observed during stellar birth appears again during stellar death. As matter occupies a much smaller volume, rotational speed tends to increase. Not every white dwarf rotates rapidly. Various processes during stellar evolution can redistribute angular momentum before the remnant forms. Nevertheless, many white dwarfs spin significantly faster than their parent stars once did. Some complete a rotation in hours, others rotate even more quickly. The dense nature of white dwarfs makes them fascinating laboratories for studying rotational physics. A teaspoon of white dwarf material would possess an enormous mass by everyday standards. Gravity at the surface is correspondingly intense, Yet despite these extreme conditions, the remnant continues carrying angular momentum inherited from earlier stages of stellar evolution. Some white dwarfs exist in binary systems where a companion star remains nearby. In such cases, material can flow from the companion onto the white dwarf. This transfer carries angular momentum as well as mass. As a result, the white dwarf may spin faster over time. Astronomers observe systems where rotational behavior reflects a long history of gravitational interaction between stellar companions. An even more dramatic outcome occurs when a massive star reaches the end of its life. Such stars eventually develop cores dominated by heavier elements. When the internal support provided by fusion becomes insufficient, gravity causes the core to collapse rapidly. The outer layers may be expelled in a supernova explosion, while the core survives as a neutron star. A neutron star represents one of the densest known objects in the universe. Its mass may exceed that of the Sun, yet the entire object occupies a sphere only a few tens of kilometers across. Matter exists under conditions far beyond anything naturally found on Earth. The collapse from a stellar core to a neutron star involves an extraordinary reduction in size. Angular momentum conservation produces a striking consequence. A massive stellar core that once rotated relatively slowly can become a neutron star spinning at tremendous speed. As the radius shrinks, rotational velocity increases dramatically. The effect resembles the acceleration of a rotating skater, drawing arms inward but on a scale almost beyond imagination. Some newly formed neutron stars rotate many times each second. Others spin even faster. Among the most remarkable examples are pulsars rotating neutron stars that emit beams of radiation. If one of these beams sweeps across Earth during rotation, astronomers observe regular pulses. The discovery of pulsars provided one of the clearest demonstrations of extreme stellar rotation. Certain pulsars rotate with astonishing precision. Their pulses arrive so regularly that they rival the accuracy of some of humanity's most sophisticated clocks. The stability reflects the extraordinary rotational consistency of the neutron star itself. Millisecond pulsars represent particularly rapid rotators. These objects complete hundreds of rotations each second. Many acquire such speeds through interactions with companion stars. Material transferred from the companion carries angular momentum onto the neutron star, gradually accelerating its rotation over millions of years. Despite their rapid spin, neutron stars remain governed by the same physical principles observed throughout the cosmos. Angular momentum is neither created nor destroyed. It is redistributed, concentrated, and transferred between objects. The extreme rotational speeds arise because enormous amounts of angular momentum become confined within extraordinarily small volumes. Rotation strongly influences neutron star behavior. Rapid spin affects magnetic fields, radiation emission, and interactions with surrounding matter. In some cases, the magnetic field becomes trillions of times stronger than Earth's. The combination of intense gravity, strong magnetism, and rapid rotation creates environments unlike any other known in astronomy. Observations reveal that neutron stars gradually lose rotational energy over time. As radiation escapes and magnetic processes operate, spin rates decrease slowly. The effect can be measured through careful monitoring of pulsar signals. Even these extraordinarily stable rotators evolve as they age. Occasionally, astronomers observe sudden changes in neutron star rotation known as glitches. During a glitch, the rotational speed increases slightly over a very short period. Researchers believe these events arise from complex processes within the star's interior. Observations indicate that the outer layers and deeper regions may not always rotate in perfect synchrony. The exact mechanisms remain areas of active study. White dwarfs and neutron stars demonstrate how rotation behaves when gravity compresses matter to extraordinary densities. Ordinary stars already rotate, but compact remnants reveal the consequences of carrying angular momentum into much smaller dimensions. The result is some of the fastest sustained rotational motion found anywhere in the universe. These objects also highlight an important theme. Rotation does not disappear when stars die. Instead, angular momentum survives the transformation. It adapts to new conditions and often becomes more apparent than before. The collapse of a star concentrates motion into increasingly compact forms, preserving the rotational history of earlier stages. Across the galaxy, countless white dwarfs and neutron stars continue turning through space. Some rotate quietly, others emit precise pulses detectable across immense distances. All preserve evidence of angular momentum inherited from their stellar ancestors. Through them, the universe demonstrates that even the most dramatic changes in structure and density do not erase the tendency towards spin. Instead, rotation remains present, often becoming more extreme, as gravity compresses matter into some of the most compact objects known. Among all known astronomical objects, black holes represent some of the most extreme manifestations of gravity. They contain so much mass concentrated within such a small region that escape becomes impossible once matter passes beyond a boundary known as the event horizon. Light itself cannot return after crossing this limit. Despite their reputation for mystery, black holes follow the same physical laws governing the rest of the universe. Angular momentum remains one of those laws. A black hole can possess mass. It can possess electric charge, though most astrophysical black holes are expected to have very little net charge. It can also possess angular momentum. When a black hole rotates, the effects extend beyond the event horizon and influence the surrounding spacetime itself. The idea may seem unusual because rotation is often imagined as an object turning through space. In the case of a black hole, the situation becomes more complex. According to the theory of general relativity, gravity is not merely a force acting across empty space. Instead, mass and energy influence the geometry of space-time. Objects move within that geometry. When a black hole rotates, its angular momentum affects the surrounding space-time. The rotation effectively drags nearby space-time along with it. This phenomenon is known as frame dragging. Observations and theoretical calculations indicate that rotating masses can produce such effects, although they become especially significant near rapidly rotating black holes. The origin of black hole spin follows a familiar pattern. Most stellar mass black holes form from the collapse of massive stars. Before collapse, the star already possesses angular momentum. During the transformation, much of that angular momentum survives. Because the resulting object occupies a far smaller region, rotational effects become concentrated. A newly formed black hole therefore inherits rotational characteristics from its parent star. The precise spin depends on factors such as the original stellar rotation mass loss during evolution and conditions during collapse. Different black holes emerge with different rotational states. Astronomers cannot observe black holes directly because no light escapes from within the event horizon. Instead, they study the influence black holes exert on nearby matter. One of the most important clues comes from accretion disks. An accretion disk forms when gas dust or other material approaches a black hole while possessing angular momentum. Rather than falling directly inward, the matter begins orbiting. Friction and other processes within the disk gradually redistribute angular momentum, allowing material to spiral closer to the black hole. These disks often become extraordinarily hot. As matter moves inward, gravitational energy converts into heat and radiation. The resulting emission can outshine entire galaxies in certain circumstances. Observations of these luminous environments provide information about the properties of the central black hole, including its spin. Measurements indicate that many black holes rotate rapidly. Some appear to spin at rates approaching the theoretical maximum permitted by general relativity. Such conclusions arise from detailed analysis of radiation emitted by matter near the event horizon. While uncertainties remain for individual objects, observations strongly support the existence of rapidly rotating black holes throughout the universe. The influence of rotation extends beyond the disk itself. In some systems, powerful jets emerge from regions near the black hole. These jets consist of particles accelerated to enormous speeds and expelled across vast distances. Certain jets extend for thousands or even millions of light years. Researchers believe that black hole spin may contribute significantly to jet formation. Magnetic fields threading the accretion disk interact with the rotating spacetime around the black hole. Energy associated with rotation can be transferred outward, helping power the jets. Observations support this general picture, though many details remain active areas of research. Supermassive black holes provide another remarkable example. These enormous objects occupy the centers of most large galaxies. Their masses range from millions to billions of times that of the Sun. Evidence indicates that many rotate as well. The supermassive black hole at the center of the Milky Way, known as Sagittarius A star, appears to possess angular momentum. Observations continue refining estimates of its rotational properties. Similar studies of other galactic centers reveal widespread evidence for spinning supermassive black holes. The rotational histories of these giants are often complex. They may grow through the accumulation of gas over billions of years. They may merge with other black holes during galactic collisions. Each event transfers angular momentum into the system. As a result, present-day spin reflects an extended history of cosmic evolution. Black hole mergers provide particularly dramatic examples of angular momentum conservation. When two black holes spiral together and merge, they emit gravitational waves. Ripples in spacetime predicted by general relativity are now directly observed. These waves carry energy and angular momentum away from the system. The final black hole inherits the remaining angular momentum after the merger. Observations from gravitational wave detectors reveal that many merged black holes continue rotating afterward. The process demonstrates once again that angular momentum remains conserved even under the most extreme conditions known. One striking aspect of black hole physics is that rotation becomes inseparable from gravity itself. In planets and stars, rotation influences shape magnetic fields and motion. Near black holes, rotation alters spacetime geometry. The distinction between motion and gravity becomes increasingly intertwined. Despite their exotic nature, black holes reinforce the same theme encountered throughout the cosmos. Rotation does not emerge only in ordinary environments. It persists under conditions involving immense gravity, extreme density, and relativistic effects. The same principle that shapes galaxies, stars, and planets continues operating here. Across the observable universe, black holes carry angular momentum inherited from collapse accretion and merger events. Their spin influences surrounding matter powers energetic phenomena and modifies the structure of spacetime itself. Even at the threshold where gravity becomes most intense, the tendency toward rotation remains present, demonstrating that angular momentum is not merely a common feature of cosmic objects, but one of the deepest organizing principles governing their evolution. The rotating galaxies, stars, planets, and black holes observed throughout the universe all possess histories that stretch far into the past. Their angular momentum did not appear suddenly after these objects formed. Instead, the origins of cosmic spin reach back toward the earlier stages of structure formation. To understand why rotation is so widespread, attention turns from individual objects to the young universe itself. Shortly after the beginning of cosmic expansion, the universe differs greatly from the one observed today. Galaxies do not yet exist, stars have not formed, planets are absent. The matter that will eventually become these structures remains distributed in a much simpler state. Yet even in this early environment, the conditions that later generate rotation are already present. Observations of the cosmic microwave background provide an important window into this period. This faint radiation fills the entire sky and represents light released when the universe became transparent hundreds of thousands of years after expansion began. Careful measurements reveal an extraordinary degree of uniformity. Temperatures appear nearly identical in every direction. At the same time, the cosmic microwave background is not perfectly uniform. Tiny variations exist. Some regions are slightly denser than average, others are slightly less dense. The differences are extremely small, but they prove enormously important. Without them, galaxies and larger structures would never form. These slight density variations act as seeds for future cosmic evolution. Gravity gradually amplifies them. Regions containing a little more matter attract additional material. Over millions and billions of years, those regions grow increasingly prominent. Eventually, they become the foundations of galaxies' clusters and the larger structures of the cosmic web. The early universe therefore contains irregularities from the beginning. Perfect symmetry does not exist. Matter is distributed almost uniformly, but not exactly uniformly. This fact becomes crucial because rotation emerges most naturally when symmetry is imperfect. If matter collapsed toward a central point with flawless symmetry, little or no angular momentum would develop. Real cosmic structures do not form under such idealized conditions. Small differences in density, position, and motion ensure that collapse proceeds unevenly. Material approaches growing structures from multiple directions. Slight offsets occur naturally. Researchers study these processes using large cosmological simulations. The simulations begin with conditions consistent with observations of the early universe. Tiny density fluctuations are introduced according to measured patterns. Gravity then shapes the evolving matter distribution over billions of years. The results closely resemble the large-scale universe observed today. Galaxies form, clusters emerge, filaments connect enormous regions. Most importantly, for the story of rotation, angular momentum develops naturally during the process. One influential explanation is known as tidal torque theory. In simple terms, neighboring concentrations of matter exert gravitational influences on one another, while structures are still forming. These interactions create torques that generate angular momentum. The process begins before galaxies fully exist and continues during their growth. A torque changes rotational motion. On Earth, pushing a door near its handle produces a turning effect. In the young universe, gravity provides the equivalent influence. Matter concentrations pull on one another unevenly. The resulting torques gradually impart angular momentum to developing structures. According to this picture, the first significant rotational tendencies arise not after galaxies are complete, but during their formation. Protogalaxies, the precursors of modern galaxies, acquire angular momentum through gravitational interactions with their surroundings. The effect may be modest initially, yet it establishes the rotational foundation upon which later evolution builds. Observations and simulations broadly support this framework. While many details remain under investigation, tidal torques appear capable of explaining much of the angular momentum observed in galaxies today. The theory does not require unusual events or special initial conditions. Rotation emerges naturally from ordinary gravitational interactions acting on slightly irregular matter distributions. Dark matter participates in this process as well. Because dark matter dominates the mass of many structures, its gravitational influence strongly affects angular momentum generation. Dark matter halos acquire spin through tidal torques and other interactions. Ordinary matter later falls into these halos and inherits part of their rotational motion. The early universe therefore provides the initial conditions from which later spin develops. Tiny fluctuations create uneven distributions. Gravity amplifies those differences. Neighboring regions interact. Angular momentum begins accumulating long before stars or planets appear. An important point emerges from this picture. The universe does not require an overall rotation to produce rotating structures. Observations continue to indicate that the observable universe lacks a global spin. Yet local rotation develops naturally because the conditions for generating angular momentum exist everywhere. This distinction helps resolve an apparent paradox. A non-rotating universe can still contain countless rotating objects. The key lies in local asymmetries. Small variations in density and motion allow gravitational interactions to generate angular momentum on regional scales without requiring the entire cosmos to rotate. Researchers continue investigating the earliest moments of cosmic history. Some questions remain unresolved. Observations reveal the density fluctuations present when the cosmic microwave background formed, but the ultimate origin of those fluctuations remains connected to processes occurring even earlier. Current models provide strong explanations, yet aspects of the very earliest universe continue to be studied. What remains clear is that by the time structure formation begins in earnest, the ingredients necessary for generating rotation already exist. Tiny irregularities have been established. Gravity is ready to amplify them. Angular momentum can emerge as matter gathers into increasingly complex structures. The young universe therefore represents the starting point of a long chain of events. Minute density differences evolve into galaxies. Galaxies give rise to stars. Stars produce planetary systems. Throughout this progression, angular momentum passes from one stage to the next. Rotation becomes increasingly visible, but its roots lie in conditions established long before the first stars illuminated the cosmos. By tracing the story back to these early epochs, it becomes apparent that cosmic spin is not an isolated phenomenon, appearing only in mature astronomical objects. Instead, it originates within the fundamental processes through which structure itself emerges from the nearly uniform conditions of the young universe. After examining galaxies, stars, planets, compact remnants, black holes, and the early stages of cosmic structure formation, a common principle appears repeatedly. Every scale reveals motion that persists through change. Clouds collapse, stars form planets, assemble galaxies, merge, and black holes grow. Yet throughout these transformations, angular momentum continues to appear and endure. The reason lies in one of the most fundamental conservation laws in physics. A conservation law describes a quantity that remains constant under specific conditions. Such laws occupy a central place in modern science because they allow researchers to understand how systems evolve through time. Energy is conserved. Momentum is conserved. Angular momentum belongs to the same family of foundational principles. Angular momentum describes rotational motion. More precisely, it measures how strongly an object or system tends to continue rotating. The quantity depends upon both mass distribution and motion. A large object rotating slowly may possess substantial angular momentum. A smaller object rotating rapidly may possess a comparable amount. What matters is the combination of mass distance from the rotational axis and velocity. The importance of angular momentum lies not merely in its existence but in its persistence. When external influences are absent or balanced, the total angular momentum of a system remains constant. It can move from one component to another. It can become concentrated or dispersed. Yet it is not simply created from nothing or destroyed without consequence. This principle operates across every scale examined throughout the universe. When gas gathers into a molecular cloud, angular momentum already exists within the incoming material. During collapse, the cloud becomes smaller, while conserving most of its rotational motion. The result is faster rotation and the formation of disks. When stars emerge from those disks, they inherit part of the angular momentum. The remaining motion persists within surrounding material that later forms planets. Planetary systems provide clear examples of angular momentum transfer. Planets orbit stars. Moons orbit planets. Tidal interactions gradually redistribute rotational motion and orbital motion. Earth slowly transfers angular momentum to the Moon's orbit. The total amount remains conserved even though individual components change. The same principle governs galaxies. Material flowing into a growing galaxy carries angular momentum. Mergers redistribute it among stars' gas and dark matter. Rotational patterns evolve while respecting the broader conservation law. Even dramatic interactions do not eliminate angular momentum, they merely rearrange it. Compact objects demonstrate the principle in especially striking ways. When a stellar core collapses into a white dwarf or neutron star, its size decreases enormously. Angular momentum conservation causes rotational speed to increase. The dramatic acceleration reflects the persistence of rotational motion during gravitational contraction. Black holes provide another example. Matter spiraling inward transfers angular momentum through accretion disks. Merging black holes exchange and emit angular momentum through gravitational waves. Yet the total accounting remains consistent. Conservation continues operating even under extreme relativistic conditions. The universality of angular momentum conservation arises from a deeper feature of nature. In modern physics, conservation laws are closely connected to symmetries. A symmetry means that certain properties of the laws of physics remain unchanged under specific transformations. For angular momentum, the relevant symmetry involves rotational invariance. The fundamental laws of physics do not depend upon the direction in which an experiment is oriented. A physical process behaved according to the same rules, whether it occurs facing one direction or another. Because nature shows this rotational symmetry, angular momentum is conserved. This relationship represents one of the profound insights of theoretical physics. Conservation is not merely an observed coincidence. It emerges from the structure of the laws governing the universe. Rotational symmetry and angular momentum conservation are deeply linked. The consequences become visible everywhere. Perfect stillness is rare. Perfect symmetry is rare. Small motions and asymmetries arise naturally during structure formation. Once angular momentum appears, conservation ensures that it remains an important part of future evolution. Researchers often describe angular momentum as a quantity that systems resist losing. Removing it generally requires transferring it elsewhere. Gas falling toward a star must shed angular momentum before reaching the center. Matter approaching a black hole must redistribute angular momentum through an accretion disk. Even planetary formation depends upon mechanisms capable of moving angular momentum between different regions. This requirement explains why rotating structures are so common. Gravity gathers matter efficiently, but gravity alone does not erase angular momentum. Instead, collapse often concentrates rotational effects. As structures become smaller, spin becomes more apparent. The universe repeatedly transforms gentle motions distributed across large regions into more noticeable rotation within compact objects. Computer simulations reinforce this understanding. Whether modeling galaxy formation, stellar birth, planetary evolution, or compact remnants, researchers consistently find angular momentum conservation shaping outcomes. Simulations that ignore it fail to reproduce observed reality. Simulations that respect it generate structures resembling those seen through telescopes. Observations confirm the same conclusion. Rotational motion appears across a staggering range of scales. Galaxies hundreds of thousands of light-years wide rotate. Planets thousands of kilometers across rotate. Neutron stars only a few tens of kilometers wide rotate. The enormous differences in size conceal a common physical foundation. An especially revealing aspect is that angular momentum often survives events that dramatically alter other properties. A cloud becomes a star becomes a white dwarf, a massive star becomes a neutron star or black hole. Matter changes state, density changes, temperature changes, yet angular momentum remains part of the story. The persistence of spin therefore reflects more than coincidence. It reflects a conservation law woven into the structure of physical reality. Whenever asymmetries create rotational motion, that motion tends to endure. It may change form, it may move between objects, it may become concentrated or dispersed, but it remains present. Across the observable universe, countless processes unfold simultaneously. Galaxies evolve, stars age, planets orbit, black holes merge. Beneath this diversity lies a shared principle connecting every scale. Angular momentum conservation provides continuity amid change, ensuring that rotational motion survives. The transformations through which cosmic structures form, evolve, and sometimes disappear. After moving from the largest cosmic structures to the smallest astronomical systems considered in this journey, a consistent pattern stands out. Rotation is not confined to a particular category of object. It is not limited to planets, stars, galaxies, or black holes alone. Instead, spin appears across nearly every level of cosmic organization. The question posed at the beginning of the exploration now reaches its deepest answer. Why does almost everything in the universe spin? The explanation does not depend upon a single event. No universal engine sets all objects rotating. No evidence indicates that the observable universe itself spins as a whole. Observations continue to support a cosmos that expands in every direction, without displaying a detectable global rotation. Yet within that expanding universe, local structures repeatedly acquire angular momentum. The reason begins with the nature of cosmic structure formation. Matter in the young universe is distributed almost uniformly but not perfectly. Tiny fluctuations in density exist from the earliest observable times. Gravity gradually amplifies those irregularities. Regions containing slightly more matter attract additional material. Structures begin to emerge. Crucially, the process is never perfectly symmetrical. Material approaches growing structures from different directions. Velocities differ slightly. Neighboring concentrations exert uneven gravitational influences. Small offsets become unavoidable. These asymmetries create the conditions necessary for angular momentum to appear. As galaxies, clouds, and other structures form, gravitational interactions generate rotational motion. Tidal torques transfer angular momentum into developing systems. Matter falls inward, carrying both radial and sideways motion. Rotation emerges naturally as a consequence of uneven collapse within a gravitationally evolving universe. Once angular momentum exists, conservation ensures its persistence. This conservation law provides the second essential part of the explanation. Rotational motion cannot simply vanish. It may move between different parts of a system. It may be redistributed through collisions, tides, magnetic fields, or gravitational interactions. Yet the total angular momentum remains conserved under the governing laws of physics. As a result, the angular momentum generated during early structure formation survives through later stages of evolution. A molecular cloud inherits motion from the galaxy around it. A forming star inherits motion from the cloud. A planetary system inherits motion from the rotating disk surrounding the young star. Each stage passes angular momentum forward while transforming its appearance. Gravity often makes the effects more visible. When a structure contracts, its size decreases. Angular momentum conservation then tends to increase rotational speed. This principle explains why compact objects can spin so rapidly. White dwarfs rotate faster than many ordinary stars. Neutron stars may rotate hundreds of times each second. The same law operating within a slowly rotating cloud ultimately helps produce some of the fastest rotators in the universe. The widespread presence of spin therefore reflects a partnership between gravity and angular momentum conservation. Gravity gathers matter into structures. Angular momentum influences how those structures evolve. Together they create rotating galaxies, rotating stars, rotating planets, and rotating compact remnants. Another important insight emerges from this understanding. Rotation is not an unusual outcome requiring special circumstances. In many situations, the absence of spin would be more surprising than its presence. Perfect symmetry is extraordinarily difficult to achieve. Tiny asymmetries arise naturally. Once they do, angular momentum tends to develop and persist. Computer simulations reinforce this conclusion repeatedly. Researchers begin with conditions matching observations of the early universe. Gravity acts on matter over billions of years. Without imposing rotation, artificially spinning structures emerge. Galaxies rotate. Disks form. Stars acquire angular momentum. The results resemble the real universe because the underlying physics naturally favors the development of rotational motion. Observations support the same picture. Telescopes reveal rotation across a remarkable range of scales. Entire galaxies turn through space. Molecular clouds rotate before stars form. Young stars emerge within rotating disks. Planets spin around their axes while orbiting their stars. Compact remnants preserve and often amplify inherited angular momentum. Black holes influence space-time through their rotation. Even smaller systems reflect the same tendency. Asteroids rotate. Comets rotate. Ring particles orbit within rotating structures. Angular momentum appears so consistently that it becomes one of the defining features of cosmic evolution. Yet the story remains elegant in its simplicity. The universe does not require separate explanations for every spinning object. Instead, one broad framework connects them all. Small asymmetries generate angular momentum during structure formation. Gravity amplifies the consequences. Conservation preserves the resulting motion. From that combination emerges the extraordinary diversity of rotating systems observed today. Some details remain subjects of ongoing research. Scientists continue investigating the precise histories of individual galaxies, stars, and black holes. They study how angular momentum moves through complex environments. They seek deeper understanding of dark matter and the earliest moments of cosmic history. Certain questions remain unresolved. Observations indicate how rotation develops across cosmic scales. It remains uncertain exactly how every detail unfolds in every individual system. The universe is too varied for a single simple description to capture every case. Yet the overall pattern is strongly supported by evidence gathered through observation theory and simulation. The deepest answer, therefore, does not point toward a mysterious force uniquely responsible for spin. Instead, it points toward ordinary physical laws operating over extraordinary spans of space and time. Gravity shapes structure. Asymmetry creates angular momentum. Conservation preserves it. Together, these processes transform a nearly uniform young universe into a cosmos filled with rotating structures. Across billions of galaxies and countless stars, planets, moons, asteroids, comets, neutron stars and black holes, the same principles continue working. Every turning world and every rotating galaxy carries part of a story that began with tiny irregularities in the early universe and unfolded through billions of years of cosmic evolution. The remarkable prevalence of spin is therefore not an exception to the rules of nature. It is one of the clearest expressions of those rules. Almost everything spins because the universe forms structures through processes that naturally generate angular momentum, and because the laws of physics ensure that once that motion appears, it endures. The observable universe settles into a quieter perspective when viewed across the immense span of cosmic time. Galaxies continue rotating, stars continue turning, planets maintain their steady motion around distant suns. Yet the scale of these processes places them beyond ordinary human experience. Their movements are constant but patient, unfolding across intervals measured in millions and billions of years. A galaxy completes another fraction of an orbit around its center. A star slowly loses a small amount of angular momentum through its stellar wind. A moon continues its tidal exchange with the planet it accompanies. Far away, a neutron star turns countless times while preserving a rhythm established long ago. None of these events requires urgency. The universe proceeds according to physical laws that remain steady across vast distances and immense durations. The tendency towards spin reveals itself not as a separate force, but as a consequence of how structure forms and evolves. Matter gathers, small asymmetries persist, gravity shapes the outcome, angular momentum survives. The result is a cosmos in which motion becomes part of the identity of nearly every object. Even the most familiar experiences reflect this larger reality. Earth rotates through day and night. It travels around the sun. The sun circles within the Milky Way. The galaxy moves within a larger cosmic environment. Motion exists at every scale, often unnoticed, because it remains so continuous. Across the observable universe, countless rotations occur simultaneously. Most will continue long after any individual observer is gone. Stars will age, galaxies will evolve, new structures will form from old material. Through these changes, angular momentum will continue passing from one generation of cosmic objects to the next. The story ultimately becomes one of continuity. The same principles operating in vast clouds of interstellar gas influence planets and stars. The same conservation law governing a rotating galaxy also governs a spinning neutron star. Enormous differences in scale do not erase the underlying connection. In the calm darkness between the stars, matter continues following paths established by gravity and motion. The universe remains active without haste, dynamic without urgency. Across its immense expanse, countless objects continue their steady turning, preserving a record of ancient motions carried forward through time.